Welcome. Today's lesson is on chemical bonds. We're going to start today by talking about the different types of bonds. There are three types. There's covalent, ionic, and metallic. I'm not going to talk about metallic bonds today. That's going to be for another video. But I want to first of all share with you the different kinds of covalent bonds there are. There are basically two kinds, polar and nonpolar. When we look at covalent bonds as a whole, it's really the sharing of electrons that's important to know about in covalent bonds. There is a polar type. This is the polar covalent bond shares its electrons much more unevenly, and one side of the compound it's a little bit more negative than the other one, like water. The other covalent bond is a nonpolar covalent bond, where it is shared a little bit more evenly throughout the entire compound. Then we also have ionic bonds. Instead of sharing them, they basically transfer them. One of the elements, or some of the elements, will want those electrons more than the other ones that are in that compound as well. So, but before we move on to the actual how do we know what kind of bond they're going to get by looking at their elements, we're going to first of all talk about this rule, the Octet Rule. The Octet Rule basically says that all the elements want their 8 electrons on the outside to be stable. In this example, carbon dioxide, the oxygen brings 6 electrons to the party. And that's the third one, the fourth one, the fifth one, and the sixth one. It needs 2 more electrons out in the outer valence. And carbon is more than happy to provide it, because if it has 2 oxygens, then it will also have, because really carbon has 4 to share, and if it gets 2 to one side, like on this example, and 2 to the other side, then everybody's happy. So for instance, for the carbon, it gets what it wants, the 2 extra ones on one side and 2 extras on the other. So it has 8 in its outer valence. And then the 2 oxygens also have theirs. So the Octet Rule in this particular example is fulfilled by 8 electrons in each of the shells of these elements. Now there's another part to this, is you're going to need a kind of a special tool to be able to determine what kind of bond it is. You'll need the electronegativity chart that you'll find on the periodic table. Some more comprehensive ones will have all of them, all of the things that you need all in one sheet. But I just kind of wanted to parse out just the electronegativity in this one so it's easier to see. So the way this is organized, if you travel from the left to the right, it'll get more electronegativity. In other words, it'll have a stronger want or desire to get 1 more or 2 more electrons in its outer valence. In this case, we have fluoride. Fluoride has 7 electrons on the outside, so it only needs 1. So it's strongly electronegative. So in this example, 3.98 for the electronegativity scale for fluoride. If we go on the left-hand side and you travel from bottom to top, negativity is also go up as you go up in the periodic table. So in this case, the one that has the least amount of electronegativity will be francium. It has just 1 little electron on the outside that's floating around, and it would rather give it up than try to maintain it, because underneath that shell is a shell of 8, and it would much rather stay at that level than trying to get 7. So it's more apt to give up the 1 electron, whereas fluoride would rather just take 1 and then be happy that way. Now, before we start actually looking at all the numbers, what I want to do is I'm going to drop down some things to help you get a scale of things, such as you understand how you can put them, these compounds in different, these bonds in the compounds in different layers. In this scale, if you have a number of electronegativity between 0 and 0.5, it's a nonpolar covalent bond, which again means that it shares it more equally in all of the elements of the bonds that we're looking at today. The next scale is 0.5 to 1.7 electronegativity. Basically what that means is it's a polar covalent bond, which means one side of that compound is going to have more negativity than the other side, so it's not shared equally. And then lastly, if there's a scale between basically 0.17 and higher, then you have a strongly ionic type of bond. So let's go ahead and get started. So let's clear the deck a little bit so that we know what we're doing here. And we're going to first of all start with water, H2O. So we want to see what the electronegativity is between hydrogen and oxygen. So I'm going to circle oxygen first so you can see that it's 3.14 in electronegativity. And then we're going to look at hydrogen, and we're going to subtract 2.2 electronegativity from that, and we get a number of 1.24. If we go to the scale on the left, you'll notice that 1.24 falls in the category right in the middle of 1.7 to 0.5. That would be a polar covalent bond where it doesn't share the electrons equally. So it's a polar covalent based on the number of 1.24 and the scale that's on the left. So let's get rid of all of that. Again, clear the deck for our next, there we go, there's our next compound. We're looking at boron and we're looking at hydrogen. So I'm going to select boron first. And notice that it's a 2.04 in electronegativity. Then what we're going to take a look at is hydrogen. As we've already said before, it's 2.20. So when you subtract the two, it's 0.16. That falls in the scale between 0 and 0.5 electronegativity. And you'll notice it's going to be a non-polar covalent where it shares the electrons evenly between the elements. So let's erase all of that. And our last one that I want to show you before we sign off today, we're going to go NaCl, which basically is salt. We're going to first of all take a look at chloride, and it's 3.16 in electronegativity. The electronegativity number for sodium is 0.93. You subtract and get it at 2.23 electronegativity. I hope that has helped you, and I hope that you'll have an opportunity very, very soon to get into those practice problems. And until next time, I'll see you in the lab. Thanks. Bye.